We're on day 2 of our sequences notes. And so let's just kind of recap what we talked about before. So we can find out if a sequence converges or diverges by finding its limit. And remember, when we say a sequence converges, we mean that its terms approach a single value. I'm just going to say number. The terms approach 0, the terms approach 2, whatever it may be. If we say a sequence diverges, then I was going to write this out again, but really it's just not that, right? Like the terms either bounce back and forth between numbers, like we had one in last night's homework number 9, that was like it goes between 1 and -1 back and forth, or maybe the terms approach negative infinity or positive infinity. So there is another way to determine if a sequence converges, but this is another one of those existence theorems. So I don't know. Existence theorems always kind of drive me crazy because there's still more work to do once you figure out that something converges. But anyway, this is just an existence theorem that says, hey, this thing converges or diverges, and then you can kind of go from there. So it does not give us a value for what this sequence converges to. We would have to do that work as we've been doing. So this is called the bounded monotonic sequences theorem. Remember, monotonic means that in this case, we've been saying function, but I have it right here. The terms are always increasing or always constant, or they could be always decreasing or constant, right? So monotonic just means the same thing's happening. The terms are not bouncing up and down, increasing and decreasing. In other words, you could say like A1, this first term would be smaller than the second term, which is smaller than the third term, et cetera, et cetera. Or if it's decreasing, first term is the largest, second is smaller than that, et cetera, et cetera. Bounded just means that you have sort of an upper bound and a lower bound. Like there are real limits for which the highest number the sequence can reach is something and the lowest number the sequence could reach is something. Meaning these sequences, bounded just means they don't approach plus or minus infinity, right? So there's some sort of like a ceiling and a floor, basically. So we have an upper bound and we have a lower bound. And so if a sequence is both bounded and monotonic, then it converges. Now, you don't have to be bounded above and below, but if your terms are increasing, so they are increasing, then there's got to be a ceiling. You've got to be bounded above, upper bound. If your terms are decreasing, there's got to be a floor to hit, so you've got to have a lower bound. All right, so let's look at some of these. Again, this is just an existence theorem, so it just helps us decide whether we should even be bothering to take limits and things like that. All right, now we had this example in the first day's notes, I believe, where we said if we actually list out some of these terms, like if n is 1, we get 2, if n is 2, we get 4. This is just going to keep bouncing back and forth. Okay, so we know that yesterday we figured out this thing diverges. Let's just kind of check to see, does it diverge according to our monotonic and bounded theorem? So is this monotonic? No, because the terms are not always increasing or decreasing. They keep going back and forth. So it's not monotonic. As soon as you break one rule, that means that theorem is going to say, okay, this thing diverges. Is this bounded? Yes, this is bounded. It has a lower bound, has a floor, right? The terms will never get any lower than 2, and it has an upper bound. The terms will never get any higher than 4. So this is a bounded sequence. It's just not monotonic. So since it's not both, then that's another way, using this theorem, using this bounded monotonic sequence theorem, I could say, oh, it diverges. But it's much easier just to list out the terms on this one and say, oh, diverges. Doesn't approach one single value. All right, what about this next one? So again, if I'm actually figuring out if this converges, what does it converge to, I'm not going to bother with the monotonic bounded sequence. I'm just going to say, let's just take the limit of this thing, oops, and see what happens. The limit as n approaches infinity of 2n over 1 plus n. This is a tie. It's 2. So yeah, this converges. But we're going to check it based on that theorem because, again, maybe this theorem pops up somewhere. We have to be able to reference it. So, all right, so is this monotonic? Are the terms decreasing? How do I test if something is monotonic? Remember, if something's monotonic, we said that each term, like the first term would need to be less than the next term or whatever. And how do I decide if I think this is decreasing or increasing? Start just by listing out some terms. So when n is 1, what do you get? You get 2 over 2, which is 1. When n is 2, you get 4 over 3. So the terms increased from 1 to 2, but then the third term, I get 6 over 4. Let's see. So this is like 1.3-ish, right? This is 1.5, 1.5-ish. What if I put in 1, 2, 3? What if I put in 4? 8 over 5. What's that? That's 1.6, right? Okay, so these do appear to be increasing, right? So if I suspect increasing, then that means that, how do I compare these two terms? Here's the, let's just call this the first term, compare it to the second term, or previous term to the next term. If this is increasing, the previous term is less than or equal to the next term. Well, how do you test this according to what we have? Well, b sub n is 2n over 1 plus n. B sub n plus 1 would be putting n plus 1 in for n in the sequence. Oops, 1 plus n plus 1, 1 plus that. Okay, so now what am I looking at? Well, I'm looking at 2n over 1 plus n is less than or equal to 2 times n plus 1 over n plus 2. All right, well, how do I figure out if that's true or not? Basically, you can just say cross multiply. You can say 2n times n plus 2, that's 1 plus n plus 1, should be less than or equal to 2 times, I guess this would be n plus 1 squared. All right, and we can keep working this out. 2n squared plus 4n, is that always less than or equal to, do this off to the side so I don't have to write it again, squaring that out, distributing 2 through, 2n squared plus 4n plus 2. It's easier to see here that yes, that is always true because this number is less than or equal to this number, the same number, plus 2. So yes, that's true. Ooh, okay, so that's a lot of work to say, hey, this is a monotonic sequence. All the terms are increasing. Is it bounded? If the terms approach infinity, then it doesn't matter that they're increasing the whole time because they're not bounded. So since they're increasing, I just care about an upper bound. Is there an upper bound that I'm hitting? Yes, if you're checking this, you can check it numerically. But again, to figure out the bounded piece, you're kind of just taking the limit, which is ultimately what the original problem was. So that's why I am not a huge fan of this theorem. Like, yeah, there's a bound. It's 2. The upper bound is the limit because that's what we're trying to do, right? So again, this is not my favorite theorem, but I feel like I've seen it referenced in a place or two, so we do need to check. All right, let's check out C sub n. So first list out some of the terms. Start with 1. 1 over 2 minus 1. 1 over 1 is 1. Put in 2. 4 over 4 minus 1 is 4/3. Put in 3. 9 over 7. Put in 4. 16 over 2 to the 4th is 16 minus 1 is 15. So we're at 1 1 1/3, 1 2/7, 1 1/15. This is definitely getting smaller. It's like 1 and something. All right, so the question is it actually monotonic or not? So it seems like this thing is bounded, and it seems like it's never going to get lower than 1, right? So let's look at this. Let's see. So can we check for monotonic? And we suspect it's decreasing. So that means that the previous term should be greater than or equal to the next term. All right, so this would be n squared over 2 to the n minus 1 is greater than or equal to n plus 1 squared over 2 to the n plus 1 minus 1. Cross multiply. Now 2 to the n plus 1 is 2 times 2 to the n minus 1 in parentheses times n squared, greater than or equal to 2 to the n minus 1 n plus 1 squared, 2 n squared times 2 to the n minus n squared, greater than or equal to, this is going to be n squared plus 2n plus 1. Whoa, goodness, we get to FOIL this through. So this is going to be n squared times 2 to the n plus 2n times 2 to the n plus 2 to the n minus n squared plus minus 2n minus 1. I have this term